My name is Jay Yuan. I have 25 years in the packaging industry, and I got my PhD for continue computational mechanics 25 years ago. So since then, I mainly work in the consumer industry and packaging from flexible to rigid, from glass to metal to paper. So today, I'm going to talk about the technology and the flexibles. And you can see from the experience folks and typically knows, and that they have a lot of experience by reacting. And our young folks and also reacting with their technology. So they got the same output, but it has to be the combination of the two. And so the purpose of this webinar, so we're going to talk about the technology, the simulation technology specifically, and only through a specific example. What we're going to talk about is the chip bag filling simulation. But through that, we'll demonstrate the maturity and the readiness of the simulation technology. And I also want to raise the awareness of its impact on the flexible packaging industry, consumer experience, and sustainability as a whole. So physics-based simulation technology without the traditional try and error results in cost savings and the ability to go to market faster. And in addition, vision for consumer experience and utilization of simulation to overcome the technology gaps are significant enablers and to achieve sustainability goals. So we're talking about this enabler is when we have in the development process, it is very important to have this technology enabler in the process so we can achieve the goals we want. So this is really the purpose of this webinar. So what about, so this is about, we're talking about shipping less air. And we're talking about why we even shipping air. So this is survey of 14 recognized brand names, and those are chip bags on the screen. So you can see the average air content in this bag is 43%. We do indeed shipping air around by shipping the chips. So if you talk about the even we think about the Pringles, and typically is technically it's not potato chips, and as you can see, the Pringles are listed there. Even that pretty dense potato chips, even though we cannot call it potato chips, has 28% of air. So, and when I read this article, and I understand what's this all about, and this is the article is about the consumer satisfaction and things like that. But as an expert working in the packaging industry for 25 years, I was thinking shipping truck is half empty. We are indeed shipping airs. What waste of energy, right? So going forward, and this article I mentioned about on previous slide is about consumer dissatisfaction and their perception of being cheated. And so, and there are the validity of the claim aside. So this is we have 300 in 2017 alone, 300 slack fill cases were filed. So there's just litigation. This is on 2 years span, 16 and 17. select fill meaning you don't fill the whole bags. So this select fill litigation can be really frustrating for the business at that time. So the thing is for companies yet to find themselves on the wrong side of the select fill litigation, the claim often boil down to, I thought there were more packaged, more in the package, even though the label said exactly what I was buying. So it's about the consumer perception on this. So, and this is a big deal in 2016 and 17. As you can see, the picture on the left, there's social media showing half the bag is empty and false advertisement, and very disappointed customer. And you don't want that for your brand. This is associated with your brand, but it is happening. So the from business point of view, there is a lot of money to be saved, and I did a quick research, and and this is showing just the potato chips segment alone in U.S. market in 2019. So 17 billion revenue only. We're talking about potato chips alone. We're not even talking about other snacks. And the company, what we know, company typically spend average, around 7 to 13%. So in average 10% of total sales, which is that 17 billion, the total industry, and on transportation. So do the math, it's 1.7 billion on transportation. Okay, so we're thinking we're not shipping 50% of air, let's only ship 40% of air. So that's a 10% of air content reduction. 10% reduction of 1.7 billion, that's $170 million. That's a lot of money to be saved. So just by the pure simple calculation, and there for not only for the sustainability, but for the money saving for the brand owner, there's a lot of money to be saved. So going forward on the in terms of the sustainability impact on those smaller bags, so the additional research I've done, I did a rough calculation on the CO2 emissions on the fuel usage. So if you think about it, it's on the 10%, every 10% of air content reduction in the bag, we said it's 170 million savings in transportation. 15.2% of the transportation cost is petroleum, and that's 8.9 million gallons of diesel. So we're saying the $2.90 per gallon. Actually, even more nowadays, and gasoline is cheaper. So the calculation translate to 91,000 metric tons of CO2 emission. And so if you do that calculation, so I was interviewed by the Plastic Engineer magazine twice on this article. By the way, this article was a similar topic I was presented in Plastic Society, their annual conference in March. They were asking, one of the questions is, what's 91,000 metric tons of CO2 means? That was the article when I did, that was December last year. So I did a calculation. I said, okay, for the average consumer, 91,000 metric tons of CO2 is equivalent to entire New York City standing still for 15 hours. I said to the audience back then, And guess what? And in March, when I presented this paper later on, uh, New York City is pretty much dead back then. But anyhow, the that's a lot of energy being wasted, and so a lot of CO2 can be saved. And on top of that, and when we make a smaller bag, when we talk about a 10%, and only 10%, and we're talking about 12 million chip bags. So, because in American, everybody love, or here in the states, everybody loves chips, and we 8 or more bags chips consumed per, you think per each of 15 million Americans. So you do the math, that turn out to be 12 million chip bags, and that can be saved. This is a sustainability impact just by the 10% savings of the air. So, and as packaging professionals, and we all know that I was presented to this topic to the packaging professionals, and everybody knows, and that in the audience and in that room saying, this is, we need air content, we need that. We ship air for reasons. And so, for example, we need to flush out the oxygen with inert gas using nitrogen, so to preserve the freshness of the chips. And the bag need to be large enough to avoid potential product contamination in the seal bar. So if it's too small, my seal bar can get to my heat seal can potentially crush my chips and compromise the seal. And I need those air for the pillow effect, so to protect my fragile chips during the transportation. And I also need that to prevent some spilling when open the bags. Airbag is a good thing. So as a packaging professionals, we all know those are slack fill functional, we call it function slack fill is needed. So we all know that. However, uh, is there room for less air? And there's three things. One is consumer satisfaction. We clearly see the dissatisfaction of how dissatisfaction of the consumer are. And second thing is we know the sustainability impact. So we put more material. We ship a lot of we ship empty bags, and basically the typically the truck, and on the shipping trucks they basically cubed out. They use the terminology as cubed out because they're full. They're not weighed out. You see on the highway stations, they're weigh stations. They prevent trucks to have too much weight on the trucks. And in this case, they're not weighed out because they're cubed out. So they fold 0.5% of them, half of the trucks, 50% of them are air. So this wastes a lot of energy. That's the sustainability part of it. And what we all know, we know we need those airs, the package functional need for the functional performance. Do we have a sweet spot? Can we do more to cut some slack to achieve an optimal balance on those three things: sustainability, consumer satisfaction, and packaging functional performance? Is there room for less air? So, and we're talking about the snack flexible packages on the market is sold by weight. And however, and the volume of the chips is a function of is function of the the chip broken rate, chip size, and distribution, and bag width, and back film gauge material, and line speed, all that. So the volume of all that is not function of weight, it's a function of the other things. To determine the right volume and with a given product weight is not trivial. And traditionally, they are done by trial and error process. To my best knowledge today, and the bag size is still determined just by lab testing. And what I saw my own eyes, and the engineers, the lab technicians basically fill the bags into a plastic tube, and the same they do that over and over again, and to measure the height, and then use that because they have historical data, use that to determine the height. And this is so, but they because the lack of accuracy, they have to put larger gap, a safety factor to it, put a larger bag. So due to the concern of sealing contamination and issues, the bag being too small, so those being will be corrected during the production in process, but is costly over time. And they also, and there's just more plastic films being used. And so those are the issues, and are really the challenges. And so we'll need on this specific webinar, we'll focus on the chip bag fill height only, so to demonstrate the simulation, the power of the simulation technology. So this we'll try to use is we'll try to determine the fill height and take the guesswork out of this whole equation, and by using computer modeling simulation. And this is what we call a digital twin of the actual bag filling process. Or the technology itself, we try to demonstrate the digital twin is truly identical twins and not fraternal twins. So it's the technology is mature enough and it's ready enough. We become an enabler to fast processing with the fast processing computer hardware nowadays, with the expanded modeling simulation capability, and also with big data. So organizations, brand owners, and OEMs has already accumulated tremendous amount of data, and this data can be used for validate to improve the accuracy of this modeling simulation. So it really, the study itself will try to demonstrate is we can determine the right bag size through the modeling and simulation technology. So give the example, those are or the three different cases is presented are presented here. First one is rigid round tube, which is typically the engineers use, and sometimes they use bag as well. They use the plastic tube on the left, showing the round tube. So we simulate that process. This lab process that we fill the chips in that round plastic tube. It's a rigid plastic tube, and we'll follow with 100% of the full chips. Those are triangular chips, like actually pita chips. And the second cases will also follow with 100% full chips into a flexible bag, and that we made up a bag of 22 ounces and 9-inch by 15-inch height. So the third case will mix up with broken chips. So basically, 5% of half chips and 3% of the third of chips and 2% of 1/6 of chips. So in an organization typically will have those data. So because the manufacture process and the baking process and also the conveyor lines, they know the distribution. So those data are available. So how many of them are chips? They typically are available. If it's not available in this presentation, this webinar, I'll show you there's also AI and machine learning technology can gather those data as well. Those are going to be the input to the simulation. Here's the animation showing filling to the plastic tube. This is round tube, and this is about 210 chips in the whole model, and their same chip be randomized before they get into the hopper, and each time we run it, input is randomized, and so on the left showing you the animation, and we choose one of the animation. Kind of you always have one chip lagging behind. It's kind of interesting because the contact was the corner of the hopper, and on the right showing you the result. Those are 100 times. We did 100 times differently, randomized. You can sort of see the normal distribution, and the average height is 4.19. This is 21, 22 times, and the highest gets to 4.85, and that's probably 3 times. We only run 100 times, so this is just the distribution with the height. So this is again, this is 100% full chips, and with a round plastic tube. So the height is pretty low. If you look at it, the height is pretty low. And so progression to the next case, which is we still have 100% of full chips on our all full chips, but to the flexible bag. And you can see those 100 times randomized filling process, and you can see the average is around 9.2 to 9.3, average around in that range, and your highest fill height is 9.75, and your lowest, which happens probably only twice out of 100 times, is 8.76. The important thing on this one is really the brand owners and OEMs really interested in the highest fill height, because that will determine the bag size, and at that point the seal bar is going to close, and now they want to make sure the seal bar will not clamp to the chip. So that's the 9.75, and this one is very important to the brand owners in terms of determining the bag size. Progress to the case number 3. This time we added more complication, so which is the bag's still the same and the hopper's still the same, but our chips is mixed, and which is more close to reality of mixed of full and broken chips. And in real life, and there the pitas and also curled, and we're not modeling here. So if you notice that not only you notice that the height actually in this case, we were hoping the height is going to be reduced because this different weight is the same weight. If you look at all 3 cases, because the label you have to, for the brand owner, has to satisfy the label claim, so the weight is the same. With broken chips, you would expect lower fill height, but in this case, my height actually increased. This is a surprise, but I think may need to run more times. This will only run 100 times. So may need to run more times to really see the true distribution of it. But you see also in the nominal case, and they are more concentrated in the middle. And so the other thing we noticed that it's also we choose there one case, there's one chip falling behind. It takes longer time because that transition, hopper transition to the back, because that's a sharp transition, I have a bag bouncing in the back. And that's very important in the manufacturing process. It's all about in the manufacturing process, all about cycle time. So I need, for the manufacturer, they need to pump more product in the same time. So the cycle time need to be fast. And in this case, once a while, at least for this case, in 1 out of 100 time, you will have a bag like chip lagging behind. You will have problem sealing it and probably end up in the seal bar. And the bag on the chip bag filling process, they're running so fast. 1 out of 100, you have problem, meaning every minute we will have problem. That's not good. So this is showing you have the engineers visualize the whole process and how everything works. And so they can design even not only for this one, is not only for the back size, but also how they design their hopper. And so the transition is smoother. So it's very important in that, and it gave engineer a visual of the whole process. But if you think about in real life, this is not transparent. The bag has all the label, all the color, all the marketing information, and health information all there. And hopper is not transparent neither. It's still you not be able to see anything. All you see at the end, I have a leaker. I have bag and bad bag, and this happens every minute, and which is really bad. So that those three cases presented, and I have put this in the summary, and the in this table right here, the result right here, you can see the average of the case one is only 4.25 in height because it's a plastic tube. And remember, they're all the same weight, okay? So case two, I have full chips. I got average is higher, 9.2. And the third case is I have some broken chips, is lower, which makes sense. The only, as I mentioned, the thing didn't make sense is I would expect my maximum also reduced compared to case two, but it's a little bigger. So that need a little investigation, additional investigation on that. Either we need to run more, or there's some physics behind that's got that for some reason that need to be there, and we need to understand that and to change the process and to eliminate those kind of outliers. So and this runs in all those three cases for each simulation, or take about 10 minutes using a 32 parallel processing CPUs, our high performance computer cluster. So it's not very high in today's standard. There's a lot faster cloud computing power out there. It can be the computer time definitely can be shortened, but just demonstrate is the computer resources powerful enough to handle this process. And so I'll go further to this, and that's what happens back December. And later on, we have further development on that. And so this is we include the seal bars and also drawn down bell, so we can simulate the bag coming down, and you can see now it's filling and seal bar open and close. You see the whole process of that, and the left image you see directly look into the seal bar on the sideway, and the right image is a 45-degree angle. You see it, and so uh, this is a more kind of real situation with all the mixing of the chips in here, and also with the seal bar uh, and, 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 and drawdown bar model in here. This is the latest development. So, and the additional development we can do, what we mentioned about the input, the brand owners, what I have worked with, some of them are very advanced. They already have the information input information like the broken chips, the percentage and as a normal distribution, or they all have the data. Um, so for the new product, those information might not be available for the development products. So what for future development of this work, and we can use uh, the IoT and artificial intelligence and machine learning on that, and just we can gather the information. As you can see on the left, on pre-filling process, and then we have uh, a camera looking at the chips, and then and maybe there's two cameras, one from top, one from side, and they can gather the broken chips and chip also the shape of the chips, gather those information. So this feedback loop to the simulation. So that's the pre-filling process. On the during the filling process, and we can also look at this, of course, and we have to uh, be able to look through the chips. So there it is not uncommon in the process. We have transparent, first in the development process, in the transparent bags, films. In that case, we'll be able to use probably two cameras looking from this side and looking into the paper, look at those sides, and we can see any kind of damages and occur during the filling process. And also post-filling, and I was asked, because at the end of the day, the consumer will get the bag, open the bag, and during the transportation, some of the chips will be broken. So, and how many, in terms of the consumer satisfaction, is the consumer have most of them are full chips or some of them the broken chips and things like that. If we can post filling process, and also at the end, those distribution process, we can do that kind of study as well, look at the broken chips, and that way this is use the really try to use the AI and artificial the machine learning process to give a feedback loop to uh, the baking process. And that's the next one. So this is just draw some pictures, and in terms of future development, how can we leverage the artificial intelligence and the machine learning and parallel with the digital modeling, which is we just show you those three cases, modeling simulation. How can those two add together, be to increase the efficiency and of the production process, and that's in the future. So we have line data, and we have surrogate model, we have digital model, we have AI and machine learning, and all work together and for this development. So and where we are. So we really need the collaboration from the brand owners and OEMs in terms of validate and advance this digital model. And so we already received some interest from the brand owners and some OEMs. So those are in process. Validation is in process, and the future development will include some different shapes of chips. We mentioned about the curl, the pita chips, and some other snacks. And also this is also goes to gummies and candies, and there's some interest in that as well. And for gummies and especially gummies, and those shape is well defined. The difficulty is the friction of coefficient of friction, and cause some issues. And there's also interest in powders and coffee grounds, and of course liquids as well. And so in terms of how we determine the fill height and how we can model the process. So the modeling the process is the end goal is not only the bag size, but also the quality of the seal as well, and and also improve the process, the filling process itself. It's all about visualization of the filling process, because the fill process happens so quick and so random to your eyes, but in real life this is governed by the physics, and the simulation technology is able to capture that and replay that video, which you see the image, back to you, and that itself is so powerful. You can use that to find if you can increase the efficiency, improve your production process, or the packaging itself. So it's go beyond the packaging. So there's a fill temperature as well, if you think about it, and how fill is another application. So with the higher temperature, the film will deform, not only just by the due to the weight, but also due to the elevated temperature. And more randomization on the initial conditions, because I mentioned about there's one thing, the third case we were expecting the fill height is lower, but it's somehow is higher. So maybe we lack of the randomization of the initial conditions. So we might need look into that a little bit more in terms of how the bag initially the chip was getting to the hopper. And the other thing is the nitrogen flush, and especially for potato chips, we need that nitrogen flush, and we puff up the bag, and how that the internal pressure, how that affect the filling process. And the stand-up pouch. So the way the simulation we have is, we call it the it's a vertical filling process, and there's stand-up pouches is horizontal, and so the gusset, how the gusset opens, or when you fill it, from how this 2D, the bag was initially is a two-dimensional, so it's a flat, and how this translate to the 3D, what's the volume of that, because the gusset will open and the shape is different. So there's a whole lot of science behind that one. So stand-up pouch is another one, that the future development. And next one is the failure of the flexible bags, the pinholes. So everybody, what I have seen is uh, industry trying to save money, even on the chip bags. People try to use the lightweighted bags, so the density is basically the density is lower. You basically all the films has tiny little holes inside, but inside. So, but with this downgrade of the film, and is that going to cause pinhole failures? And during, especially you have the chips has Peter chips has sharp pointies, and is that going to poke a hole to the bag? So remember, those chip bags and all oxygen sensitive, very oxygen sensitive. I mean, everybody tastes the steel chips. If they expose to not too long to the oxygen, they will become steel. It's not good. So different film thickness, different films materials. That's go without saying, because on the flexible industry, one of the single things and people worry about is a lot of things. This is a very important thing people worry about is they are not recyclable because it's multi-layer. We need that multi-layer to for the permeation of the oxygen for light sensitivity. We need that multi-layer because we need a print, we need marketing information, we need the health information, we have nutrition information in there, and we have print layer. But those multi-layer cause the film back become not recyclable, actually become a contaminant in the recycling stream. So the 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 need to make it recyclable is very high, and so different film materials, mono material, is very important. So if how can we use a monolayer material and fit into our fitting process? Is that going to work or not? So cycle time and line vibration profile go without saying. Those are the variables we want to talk. So so I want to, because we're only 15 minutes left, so I want to drive to the conclusions, and so what's key takeaways and from all this this webinar? This what we're trying to say is simulation technology is ready, but it's also rapidly evolving, and its application and impact go far beyond the backfilling and shiftless air. So one example I got, this is I got probably 2 years ago when I presented in ISTA conference, international conference. This information is probably 2-3 years old. This quantum computing is 100 million times faster. Imagine 100 million faster than what we have. And the working quantum computer is less than 10 years away. That's from Microsoft. Actually, lately I learned Google already has one. So and think about 100 million times faster, and we're talking about a 10 minutes running time. And this has become millisecond. We can run this in 10 years. So it's very with the simulation technology is ready, and we need keep in mind that. And the industry really moved towards to a full virtual packaging development system. So and the brand owners and OEMs need to embrace the technology to stay ahead. It's at the end of the day is speed to market, value to the consumers, and sustainability and to the whole wide world. And we need that message as well. With that, I'll conclude my webinar and I'll give the floor to Charlie.